2.3 is going to be about polynomials mostly, and then later on it's going to be about rational functions. So really, what is a polynomial? A polynomial is an expression, and it's made up of variables and coefficients. So those are numbers that are in front of the variable. Polynomials involve operations like addition, subtraction, and multiplication. Okay, and they have positive integer as exponents. So that's really like all the rules that make up polynomials. Now, what's important about a polynomial is that it tells us information about the function itself, but also we can look at it and determine information about the graph of that polynomial. Okay, what it looks like, and here we say how many roots it has, and we'll talk about what roots are, but mainly it gives us an idea of what the shape is going to look like just by looking at the little details. Here is a more formal definition of what a polynomial is. So if we assume or let n be a non-negative integer, and we're using these numbers a sub n minus 1, so it goes in decreasing order. It's just an index, right? And a sub n cannot equal 0. Then if we define a function f of x to be this right here, so it's just a number times x to the power n plus a sub n minus 1 times x to the power n minus 1, and so on until the indices decrease all the way to a sub 0. Okay, so this is called a polynomial. It's just a general representation for a polynomial function of degree n. And the number a sub n, the number at the very beginning, is the coefficient of the variable with the highest power. Okay, this has the name as the leading coefficient. So what are we looking for, when we're looking at a polynomial? So we want to determine if the expression, something that we're given, is or it is not a polynomial, right? That's kind of like the beginning activity, right? The intro activity. So here, let's go over a couple examples and determine here in example 1 whether we see a number that fits the criteria. So these numbers that I wrote here, we'll think of them as the exponents. So we'll go through them. We have 3, 4, 5, 6, 7. Now, what we're looking for is, are they whole numbers or integers, and are they positive? So integers, the answer is yes. Are they positive? And that's got to be all of them. And the answer is yes. So if this were the powers of a polynomial expression, then this would be a polynomial. Okay? So here in example number 2, let's see what we got. We have the number 2, 1/2, 5, 3, and 8. Now, are they integers? All of them? And the answer is no. Not all of them are integers, right? This is a fraction. It's a rational number, so it doesn't really fall in the integer category. So, okay, not integers. Are they all positive? Yes, but it doesn't matter. One of them came out to be not an integer, so this wouldn't count if they were the powers of a polynomial expression, it wouldn't count as a polynomial. It just wouldn't fit the criteria. And then example 3, we're doing the same thing. Are they integers? We have the numbers 3, -4, 2/5, and 5. So if those were the exponents or the powers of a polynomial expression, would that be a polynomial? So are they all integers? No. We have a rational number, which is 2/5. And are they all positive? And the answer is no. We have -4. So at the beginning, we're just looking at the powers and trying to determine if they fall under these two categories, or if they do pass these two criteria, right? Are they integers and are they positive? So here is a real example, I guess, using integers. So on the top, we have polynomial functions. First, we have f of x, and f of x is -3 x to the 5th power plus the square root of 2 times x to the 2nd power plus 5. So we're looking at the exponents, 5, 2. This one has an exponent, but it's really just x to the power 0. So are they integers? Yes. Are they positive? Yes. So the coefficients, which is -3, square root of 2, and 5, those can be anything. They can be positive, they can be rational, irrational. Yeah, so they can be anything. Second polynomial is g of x. G of x is defined as -3 x to the 6th power minus 3 x to the 5th power plus 18 x to the 4th power. So we look at the exponents again and try to determine, is this a polynomial? And the answer is yes. We have 6, 5, and 4 as the powers. Are they integers? Yes. Are they positive? Yes. The coefficients, once again, -3, -3, and 18, don't really affect anything. Okay, they can be whatever type of number. Below we have not polynomial functions. So capital F of x is equals to -3 times, or -3 square root of x plus square root of 2 x squared plus 5. So some of you may or may not know, whenever you have a variable under the radical, is the same thing as a exponential expression, except it's a fraction. So square root is the same thing as the 1/2 power. So just because this guy right here has a power that is not an integer, then it is not a polynomial. That's why. G of x, capital G of x, says the following: -3 over x squared plus 2x squared plus 5. So you may say, well, all the powers look positive. Yes, but because this right here is x to the -2, that right there makes it not be a polynomial. Okay? Because the power is not positive, right? It has to be not under a fraction or something like that, because it makes the power be written as a negative exponent. Okay? Next, we're going to talk about the graphs of polynomials. So polynomials of degree 2 or higher are going to have a smooth and continuous graph. So anything that has power 2 or higher, and if it is a polynomial, will have a smooth and continuous graph. So what is smooth and continuous? Smooth means the graph has rounded curves with no sharp corners. Continuous means the graph has no breaks. Think of it as you're trying to draw a graph, or a graph, and you can do it without lifting your pencil off the paper, and also you don't go over the previous line. The lines don't cross over themselves. Okay? Here are some examples of what we mean by the graph of a polynomial. So here on the first graph on the top left, this is what we mean by smooth curves. See how they're nice and rounded? No sharp corners. Same here. Also notice how there are no breaks. That means they are continuous lines from one end to the other. Okay? This right here on the top right, it's discontinuous. Because if you were trying to draw this with your pencil, you would be perhaps coming from here, going all the way up to here, and then you have to lift it up and then start over down here. So the graph has a break, therefore it's not continuous. Although it looks smooth, it is not continuous. Okay? So that's important. Then here there is a sharp corner. That makes this graph not a polynomial, although it is continuous. So those are 4 different examples, and it's pretty easy to determine what is and what is not the graph of a polynomial, right? I mean, is it smooth and continuous? Then yes, it is the graph of a polynomial. Is it broken, or does it have sharp corners? Then it will not be the graph of a polynomial. Next, let's talk about the end behavior of a graph. So what is the end behavior? What does that mean? So the end behavior of a graph of a function is what happens as you go to the left or as you go to the right. Okay, that is what we understand as the end behavior. And here we're considering polynomial functions only as when we're trying to figure out the end behavior of something. So how do we determine the end behavior for any polynomial? So of course we're assuming that the polynomial has this form, just the general form for a polynomial. Now the end behavior of it is going to depend on the leading term, which is the number that is in front of the variable with the highest power. Okay, so only the highest degree counts. And so there is a piece of information that is going to be determined by the leading coefficient test. Okay, that's going to help us figure out the end behavior of any graph just by looking at it. So, the leading coefficient test. You want to consider the polynomial where a sub n is not equal to 0, right? It's existent. There's a number other than 0 in front of x to the highest power, or whatever variable, but mostly x. So, the graph of a polynomial, if n is odd, if the power is odd, that means 1 could be thrown into here, but we're thinking power 2 or higher. So 3, 5, 7, 9, 13, 11, any odd number is going to work. So if the power is odd and the number in front of the x with the highest power is positive, then you're going to have this behavior on the left. The left leg of the polynomial is going to fall. So fall left, and then it rises on the right. We don't know what's going on in the middle. That's why we make those dotted points. It can be anything. It can be a bunch of different curves. It doesn't matter. What we're only worried about is the end behavior. Okay? Still for the odd power, but with a negative coefficient. Then you're going to get the reversed behavior. So it's going to rise on the left and it's going to fall on the right side. So these pretty much are opposite directions of each other, right? Only because the coefficient is positive or negative. Then when we have even powers, it's a little easier because they kind of point in the same direction. So if the power is even and the coefficient is positive, then you have both legs rising. The left leg rises, the right leg rises. In the middle, it doesn't matter what's happening, right? It can be power 2, 4, 6, 8, 10, 12, 20, right? Any even number you can think of. So this in the middle is going to be dependent on what the power is. Now if the power is even but the coefficient is negative, then you have both legs of the polynomial or the graph falling. So the falls left and also falls right. We don't know what's going on in the middle. It doesn't matter. For now, we're only looking at the end behavior. So, if that was too complicated, in summary, you're only looking at the leading term. That's why it's called the leading coefficient test. So, if the power is odd and the leading coefficient is positive, then you have your left leg falling, your right leg going up. If you have an odd power but a negative coefficient, then your left leg rises, your right leg falls. And then here they both point in the same direction. They just depend on whether the coefficient is positive or negative. Let's do a couple examples determining the end behavior. Example 1, we have f of x be equal to x to the third power plus 3x squared minus x minus 3. So it only is important to look at this, the leading term, because it has the highest power. So what do you guys think? If we look at it, n is 3, so it is odd. Now what is the number in front of x to the third power? What is the leading coefficient? Is 1. There's a 1 in front. We don't write it because we don't need to, but the value doesn't matter. We're looking at whether it's positive or negative. So this graph has a positive number and an odd power. So if we make a graph of it, this is what's happening, right? We have the left leg falling, stuff happens in the middle, and then the right leg is rises. Okay? Example 2. We are looking again at the leading term, and now you have to think, well, which one is it? Power 4 or power 2? Which one is larger? Hopefully you thought of that. Power 4 is larger. Then, n is equals to 4, and the leading term, leading coefficient, is the number 1 again. So we have a even power and a positive coefficient. If we draw a graph of it, both legs are pointing up. Even coefficient, even power, positive coefficient. Now example 3 is going to be a little tricky. Now if you look at it, it's a little different than all the other examples. I guess that's the purpose of it. If you look at it, everything is being multiplied with each other. This times this times this. So you would want to perhaps to think power 3. That's the highest power. I'm done. But because when you multiply everything out, you are going to have a degree 3 right here. Here's a degree of 2, or a power of 2. And then there's a 1 right here. We don't write it, but it's there. You have to add up all the powers to then have a power of 6. Okay, so the power is 6, and the leading coefficient would have been -4 times 1 times 1. So now we have a power that's even and a negative coefficient. So if we make a rough graph, is going to be both legs pointing in the same direction with a bunch of different things happening in the middle. But roughly speaking, this is going to be the graph of that polynomial. Next, let's talk about the zeros of a polynomial. What are the zeros of a polynomial? First, we want to think of a function f that is a polynomial function. Then the values of x for which f of x is equals to 0 are called the zeros of f. Those are also known as the roots or the solutions to the polynomial equation f of x equals 0. So, whatever values of x make this true, those are the zeros of the polynomial. So here, it's mostly just about algebra. Can you solve an equation, right? So here's the first example. Find the zeros of f of x, and f of x is equals to x to the third power plus 3x squared minus x minus 3. So what do we do? Maybe you've learned a couple different things in algebra or high school algebra, algebra 1, algebra 2. There are many tricks, right? But this polynomial is pretty easy. So what we want to do is rewrite it. Start factoring things out. So set it equal to 0 because that's what we're doing, right? Like that's what it says up there. Just set the function equal to 0. And so now we're going to pull x squared out of this polynomial, or that piece right there, x to the third plus 3x squared. We're factoring out the x squared. Then we're going to factor out a negative 1 from here so that we can get an x plus 3 as well. And then notice how we have 2x plus 3's. Well, that's on purpose, right? So we have x squared, and if we factor out an x plus 3, we'll get the following. X squared minus 1 times x plus 3. And if you remember from algebra, there is a zero product property. Whenever you have two things that are being multiplied to each other and they equal 0, then it must be the case that they equal 0 at different values of x, like this. So we split them and set them equal to 0 and solve for x. And so here on the left, without doing all the math, we get that x is equals to plus or minus 1. And then here we have x is equals to negative 3. So what does that mean? That means that let's try to graph it here. So obviously this is a power 3 graph, and it has a positive coefficient, so you get some graph like this, right? That's the general idea. But then, what's happening in the middle? Can we get more detail? Because we want to know what's exactly happening there. So can we do it? And now we just found all the different places where the function equals 0. So that means where it crosses the x-axis. And now we're getting more detail. Here is negative 3. Here is -1, and then this is kind of wrong, so let's fix it a little. Here is +1. That's what that means, okay? This polynomial here goes through the points 0, -3, 0, -1. I said it backwards. -3, 0, -1, 0, and then 1, 0. Right? So that's what, we're getting another level of detail. We have an idea of what the graph looks like, but then now we know the x-intercepts. So that's a step in the right direction. Alright, let's do another example where it's a little bit different. Okay? F of x is equals to -x to the 4th power plus 4x to the 3rd power. And this should be to the power 2. Okay? So, same idea as before, we're going to start just by setting it equal to 0 and factoring, right? All of them have a power 2 in them, so let's pull out x squared. Before we do that, let's pretend that we multiply both sides by -1. That way, we have the leading coefficient as a positive term. We can do that, right? Anything times 0 is still 0. So we multiplied everything by -1. And so we did that to change the sign. Now factor out x squared. So x squared minus 4x plus 4. Then we're going to factor again inside of that parentheses. And so we'll get x minus 2 times x minus 2. So I'll write it in as x minus 2 squared. And again, this is the product between two things. So we'll use the zero product property to solve for x. And we get that x is equals to 0, and then x is equals to 2. Okay? It's a little different than the previous example on a couple different levels, of course. We did skip a lot of steps. And if you don't understand what happened here, do take a second to comprehend what happened, right? Okay, so let's mark the points 0 and point 2. So this is a power 4 polynomial, right? So it's going to look something like, I'll just write off to the side, right? It should look something like this. So we know that both legs are pointing downwards because the coefficient is negative, right? The original problem is negative, of course. We always got to go back to the original to try to get any conclusion from it. So this value is where it's supposed to cross or touch the x-axis. So in this case scenario, this is what's happening. So it goes up here, touches, comes back down, touches, and then it comes back down. Kind of ugly, but that's kind of what it looks like, right? So both legs are falling, they go up, touch the 0, come back down, turn around, touch the 0 value again, and then come back down. Okay? What I mean by more techniques coming soon is more techniques on figuring out the zeros, right? These two examples were just kind of like a warm-up to try to remember factoring and how to solve for 0 and make use of the zero product property. Next, let's talk about multiplicities of zeros. So, on the previous example, we had this polynomial, and when you're trying to factor it, here's what we did. We factor out or took out the negative so that everything inside was a different sign so that we can factor it better, and we were able to rewrite it as this, right? So notice now how this term has power 2, but also this term right here has power 2. So that is valuable information when we're trying to figure out what the graph looks like or what is the behavior of it. So this tells us how many times each factor occurs, right? Like an exponent tells me how many times I got to multiply the base to itself. So that tells me how many times that 0 happens. Okay, so that on the previous example, this 0 happened twice, and then this other 0 also happens twice. That is known as the multiplicity, right? It gives us a connection between the zeros and graphs. So the multiplicity tells us if a 0 turns around or if it goes through the graph, or if the graph crosses the x-axis. Okay? So here's a more formal definition of what multiplicity is. Let's say r is just a number. If r is a 0 of even multiplicity, then the graph touches the x-axis and turns around. If r is a 0 of odd multiplicity, then the graph is going to cross the x-axis at said value. So you look at the number that you got, right, as the power of this 0, and it's going to be classified as even or odd multiplicity. And that's going to tell you whether there's a little curve that touches the x-axis and turns around in the other direction, or if it's going to go through the x-axis at said value. Let's do an example of multiplicity. So here we have f of x, and is 1/2 times x plus 1 times 2x minus 3. So, you're asking, what are we doing? So we're going to find the zeros. So set a equal to 0. So 0 equals to 1/2 x plus 1 times 2x minus 3 to the second power. Maybe you want to get rid of that 1/2. We don't have to. So what are the powers? The powers are happening. There should be a 1 there. We don't write power 1 because anything to the power 1 is just the same thing. So here's power 1, here is power 2. So if we set this equal to 0, we want to get rid of that coefficient. So if we multiply everything by 2, then we get 0 is equal to x plus 1 times 2x minus 3 to the second power. So now we can make use of the zero product property. So 0 is equals to x plus 1, and 0 is equals to x minus 3 to the second power. The reason why I dropped the parentheses here because it's to the power 1, so we don't have to keep the parentheses. So x is equals to negative 1, and then this right here, we take the square root of both sides, we get 0 is equals to 2x minus 3. We solve for x, and so we have x is equals to 3 over 2. Okay? Now the big idea here is that this is multiplicity of 1, because that was the power that was around that term, right? Power 1. This has multiplicity 2, because that's the power that was outside of that term. So if you look at this in terms of a graph, what's happening is the following. Okay, so if you add all the powers, we get power 3. Okay, and we have the graph crossing at power, well, x equals negative 1, so right here, but then also crossing here at 2/3. I'm sorry, 3/2. So multiplicity 1, that's an odd number, so that means it crosses. Okay, and then of course the end behavior of this is that the graph points downwards, right? But we know that this leg is going upwards, right? It's an odd power because 1 plus 2 is the overall powers. So it's 3, it's an odd power function. Now the multiplicity at this 0 is even, so that means there's a curve like that. It touches and it turns around. Right? And then here there's another curve. It doesn't matter at this moment, but the idea is that here it crossed and here it touched and turned around. Okay? Next, we're going to talk about the intermediate value theorem. So the intermediate value theorem just tells us about evaluating points and seeing their signs. So imagine you have a function f, and it is a polynomial function with coefficients. Now, if f at a and f at b have opposite signs, meaning that if you plug in a value a into the function and you plug in a different value b into the function, and those answers have opposite signs, then there's at least one value c between a and b. So a and b are the inputs, f at A is the output, f at B is the output, right? So here's the graph that's showing what we just explained there. The idea of this is that we're trying to figure out whether there's a root between those two, right? Because what if we don't know? So here's A, here's B. If I plug in A and I get a negative number as my answer, and I plug in B and I get a positive answer, then that means that at some point between A and B, I have to cross the x-axis. Okay? And that point right there is C. And it kind of makes sense, right? You plug in a number, is it negative or is it positive? You plug in another number, is it negative or is it positive? So if they have different signs, it must cross the x-axis at some point. Now, to finish off, let's talk about some strategies to graph polynomials. So in general, how can you graph a polynomial in an effective way? So first thing you want to do is determine the end behavior. Have a plan as to whether your graph is going to have both legs up or falls left, rises right. Whatever the condition is, make sure you're aware of the end behavior. The next thing you want to do is find x-intercepts by setting f of x equals to 0, right? Now, like we talked about earlier, if you're able to factor it in some form like this, then you want to take note on whether the power is even or odd, right? And that's going to help you determine if the power is even, then the graph touches and turns around at the value r, and if k is odd, then the graph crosses at x equals r, like we just showed in the previous example. Then another thing that's very helpful is to figure out the y-intercept, and you do that by plugging in 0 into the function. So instead of x, you plug in a 0 and you solve. You compute that, and whatever number you get is going to be your y-intercept. So with those pieces of information, we can make an even more accurate graph of said polynomial. And with that, we'll finish here for the 2.3 polynomials. Thank you for watching.